This video is made to present for Core 1 contest, competition, for outstanding research explanation, and theories of everything with popular physics influencer Mr. Kurt Jaimungal. What if black holes aren't the end of physics, but rather its most dramatic transformation? Today, we're going to explore a radical new perspective that reframes how we understand these cosmic phenomena. For decades, black holes have represented a crisis in physics, a place where our two most successful theories, quantum mechanics and general relativity, seem to break down entirely. But what if that breakdown is actually a breakthrough? What if black holes are not failures of physical law, but rather the ultimate expression of a deeper relationship between quantum uncertainty and the fabric of spacetime itself? This presentation introduces a speculative, but compelling framework, that black holes represent collective wave function collapse at cosmic scale, a place where the quantum and classical worlds engage in their most intimate dance. We propose that spacetime curvature isn't just a passive backdrop to collapse, but an active catalyst that drives quantum possibilities into definite outcomes. Rather than viewing black holes as dead ends where information vanishes and singularities destroy all meaning, we'll see them as dynamic engines, feedback systems where quantum uncertainty and gravitational collapse amplify each other in a self-sustaining loop. This is the climax of reality transformation, where the universe makes its most decisive measurements. Let's begin our journey into this new perspective. To understand why we need a new framework, let's first examine the collision that occurs when our best theories meet at the edge of a black hole. On the left side of this visualization, you see spacetime curvature from general relativity, the smooth, geometric prediction that mass warps the fabric of space and time. According to Einstein's equations, when enough mass concentrates in a small enough region, spacetime curves so dramatically that it forms an event horizon. And at the center, general relativity predicts a singularity, a point where curvature becomes infinite and physical law simply ends. But on the right side, we see the quantum reality, wave functions representing particles in superposition, governed by probability and uncertainty. Quantum mechanics tells us that infinities shouldn't exist in nature. The uncertainty principle tames the extremes, ensuring that we can never pin down position and momentum simultaneously with perfect precision. So we have a fundamental tension. The singularity predicted by general relativity represents a place where predictability ends, where spacetime itself breaks down. Meanwhile, the information paradox emerges from quantum mechanics. If information falls into a black hole and is lost forever, this violates quantum unitarity, one of the most sacred principles in physics. These aren't just academic concerns. They represent a genuine collision between our understanding of the very large and the very small. Current approaches, string theory, loop quantum gravity, quantum field theory in curved spacetime, each offers partial solutions, but none fully resolves the tension. What we need is a framework that doesn't just extend one theory into the domain of the other, but establishes a genuine reciprocity between them. The core insight of our framework rests on what we call the reciprocity principle, and it fundamentally reframes the relationship between quantum mechanics and classical reality. Usually, we think of this relationship as one-directional. Through a process called quantum decoherence, the quantum world gives rise to classical structures. Environmental interactions cause quantum superpositions to lose their interference patterns, and what emerges is the definite, predictable world we experience every day. Quantum becomes classical, that's the standard view. But the reciprocity principle asks, if quantum states can collapse into classical structures, shouldn't the reverse also be possible under extreme conditions? If the collapse of quantum superpositions produces classical reality, then shouldn't the collapse of classical structures, like spacetime geometry under extreme gravity, reciprocally induce quantum collapse? This is the revolutionary shift shown in this slide. Instead of spacetime being merely a passive stage where quantum events play out, spacetime curvature becomes an active catalyst in quantum measurement. The diamond in the center represents this transformation, a prism through which the relationship between quantum and classical is refracted into something bidirectional. In a black hole, the disintegration of classical spacetime geometry doesn't just happen alongside quantum effects. It actively enforces collective wave function reduction. The spiral symbol represents this feedback loop. Curvature drives collapse, collapse feeds back into curvature, creating a self-reinforcing cycle. This reciprocal view doesn't just reinterpret black holes. It suggests that the quantum classical boundary is not fixed, but contextual. In everyday conditions, quantum gives rise to classical. But in the extreme environment near a black hole, classical structures become so dominant that they force quantum possibilities to collapse. The relationship flows both ways. One of the most profound implications of this feedback framework is a complete reconceptualization of the black hole singularity. On the left, we see the old view, the classical singularity predicted by general relativity. This is the iconic infinite spike in spacetime curvature, a point where density and curvature diverge to infinity and all predictability ends. It's often called the dead end of physics, a place where the laws break down completely. This prediction troubled physicists for decades, because it represented a fundamental failure of the theory. But on the right, we see the new view emerging from our feedback loop model. Instead of an infinite spike, the system stabilizes into a quantum-regulated attractor state, a dynamic engine represented by the swirling spiral. Here, the feedback loop between localization, uncertainty, and curvature provides a natural regulator that prevents true singularity formation. The key insight is this: as wave function localization intensifies, so does momentum uncertainty. The resulting quantum fluctuations feed energy density variations back into the curvature, but in a way that resists infinite compression. The system doesn't collapse to a point, it settles into a dynamic equilibrium, a stable configuration where geometry and wave function collapse co-evolve. This isn't just mathematical sleight of hand. It suggests that what we call a singularity might not be a breakdown at all, but rather a quantum classical fixed point, a region where the feedback loop reaches balance. The spacetime doesn't end, it transforms. The bottom caption captures it perfectly. The singularity is replaced by a quantum-regulated attractor state, where geometry and wave function collapse co-evolve. This reframes black holes from cosmic failures into cosmic successes, places where the deepest principles of physics achieve their most intimate synthesis. This video is made to present for Core 1 contest, competition for outstanding research explanation, sponsored by popular physics YouTube influencer Mr. Kurt Jaimungal. One of the most profound implications of this feedback framework is a complete reconceptualization of the black hole singularity. On the left, we see the old view, the classical singularity predicted by general relativity. This is the iconic infinite spike in spacetime curvature, a point where density and curvature diverge to infinity and all predictability ends. It's often called the dead end of physics, a place where the laws break down completely. This prediction troubled physicists for decades, because it represented a fundamental failure of the theory. But on the right, we see the new view emerging from our feedback loop model. Instead of an infinite spike, the system stabilizes into a quantum-regulated attractor state, a dynamic engine represented by the swirling spiral. Here, the feedback loop between localization, uncertainty, and curvature provides a natural regulator that prevents true singularity formation. The key insight is this: as wave function localization intensifies, so does momentum uncertainty. The resulting quantum fluctuations feed energy density variations back into the curvature, but in a way that resists infinite compression. The system doesn't collapse to a point, it settles into a dynamic equilibrium, a stable configuration where geometry and wave function collapse co-evolve. This isn't just mathematical sleight of hand. It suggests that what we call a singularity might not be a breakdown at all, but rather a quantum classical fixed point, a region where the feedback loop reaches balance. The spacetime doesn't end, it transforms. The bottom caption captures it perfectly. The singularity is replaced by a quantum-regulated attractor state, where geometry and wave function collapse co-evolve. This reframes black holes from cosmic failures into cosmic successes, places where the deepest principles of physics achieve their most intimate synthesis. The black hole information paradox has been one of the most vexing puzzles in theoretical physics for over 40 years. Let's see how the feedback loop framework offers a resolution. The old view, shown on the left, holds that information falling into a black hole is permanently lost. Once matter crosses the event horizon, it disappears from the universe, violating quantum unitarity, the principle that information is never truly destroyed, only transformed. This created an irreconcilable conflict between quantum mechanics and general relativity. Our framework offers a fundamentally different picture, shown on the right through 3 stages: information, reorganization, and emission. First, information enters the black hole in the form of quantum states associated with infalling matter. These states carry specific configurations, correlations, and histories. Rather than being destroyed, these states enter the reorganization phase, the swirling spiral at the center. Inside this feedback loop, the collective collapse process reorganizes quantum information under the constraints of extreme curvature. The wave functions don't vanish, they are restructured. The collapse is not a loss mechanism, but a transformation process. Information is encoded in the structure of the feedback loop itself, in the dynamic interplay between localization and uncertainty. Finally, this reorganized information is released through energy emission, Hawking radiation, and potentially gravitational waves. Critically, in this framework, Hawking radiation isn't just random thermal noise. It may carry subtle imprints of the wave function reorganization that occurred during collapse. The information survives, encoded in the emission patterns. The outcome, as stated at the bottom, is profound. The paradox shifts from loss of information to transformation of information. Hawking radiation becomes a carrier of quantum memory, preserving unitarity while respecting the event horizon. This reframes the entire debate. Black holes aren't information destroyers, they are information transformers. To fully appreciate the novelty of this framework, let's position it within the existing landscape of theories attempting to merge quantum mechanics and gravity. This comparison table shows how our feedback loop model differs from established approaches. Let's go through each row. First, the view of curvature. Classical general relativity treats curvature as passive background geometry, just the stage on which physics happens. Quantum field theory in curved spacetime uses a fixed background for quantum fields. Loop quantum gravity quantizes geometry itself at the Planck scale, making spacetime discrete. Our model does something different. Curvature is an active catalyst in quantum collapse. It's not passive, not fixed, and we don't need to discretize it. Instead, continuous curvature gradients drive the collapse process directly. Second, singularity resolution. General relativity predicts singularities. Quantum field theory doesn't address them, and loop quantum gravity resolves them through quantum bounces at minimal volumes. Our model regulates singularities through feedback dynamics. The loop itself prevents infinite collapse by balancing localization against momentum uncertainty. No discretization needed, no bounces, just natural self-regulation. Third, the key conceptual difference. Classical GR treats geometry as a stage. QFT treats the influence as one way, geometry affects fields, not vice versa. Loop quantum gravity quantizes geometry itself. But our model introduces dynamical feedback between geometry and collapse. They are not separate, they co-evolve in a reciprocal relationship. This bidirectional reciprocity is what sets the framework apart. It's not about extending one theory into the other's domain. It's about recognizing that in extreme conditions, the quantum and classical worlds become inseparably coupled. The feedback loop is the physics. This positions our model as a genuinely novel approach, one built on reciprocity from the ground up. Before any mathematical formalism can be developed, we need a fundamental shift in physical intuition. This slide outlines the first conceptual leap, rethinking the wave function's relationship to spacetime. In standard quantum mechanics, we treat spacetime as a fixed, passive background. The wave function evolves according to Schrödinger's equation, but that evolution assumes space and time are just coordinates, unchanging containers for quantum dynamics. Gravity and geometry sit in the background, irrelevant to the quantum story. But if our framework is correct, this assumption breaks down in extreme gravitational environments. The wave function doesn't merely live in spacetime, it responds to spacetime. When curvature becomes intense, the geometry itself participates in quantum evolution. The shape of space actively influences how quantum states evolve and collapse. The old intuition diagram shows a simple wave function on a flat grid, a passive stage. The new intuition diagram shows the wave function on a dramatically curved spacetime fabric, with arrows indicating reciprocal interaction. The curvature isn't neutral anymore, it actively compresses, constrains, and forces the wave function into definite configurations. This shift is subtle but profound. It suggests that in black hole environments, quantum mechanics must be sensitive to geometric structure. The evolution of the wave function cannot be separated from the evolution of spacetime itself. They are entangled. Philosophically, this means the wave function doesn't simply live in spacetime, it lives with spacetime, responsive to its shape, affected by its curvature. And in the most extreme case, a black hole, this responsiveness becomes so strong that spacetime curvature acts like a measurement apparatus, forcing quantum superpositions into definite outcomes. This conceptual shift lays the groundwork for everything else. It's the foundation upon which the feedback loop is built. The second conceptual shift challenges how we think about what gravity responds to. This is where Einstein meets Heisenberg in a profound way. In Einstein's general relativity, spacetime curvature is sourced by energy and momentum. The field equations tell us precisely, matter and energy curve spacetime. This works beautifully in the classical regime where energy is well-defined, where particles have definite positions and momenta. But quantum mechanics tells a different story. In the quantum world, energy isn't always well-defined. Under the uncertainty principle, when you compress a particle's position, forcing it into a tiny region, its momentum becomes wildly uncertain. An uncertain momentum means uncertain energy. Energy fluctuates, becomes probabilistic, spreads across a range of possible values. So here's the quantum refinement shown in this slide. Under extreme localization, such as near a black hole, energy becomes intensely uncertain and fluctuates dramatically. If gravity responds to energy, and quantum energy is uncertain, then spacetime must respond not just to average energy, but to these intense quantum fluctuations themselves. The visual at the bottom captures this beautifully. The uncertainty-induced energy fluctuations create ripples in spacetime curvature. Curvature reacts to unresolved quantum tension, to the fact that the system cannot simultaneously define position and momentum. The quote in large text says it perfectly: gravity responds not only to what is, but to what cannot be decided. Spacetime curvature is no longer just responding to definite, classical energy distributions. It's responding to quantum indeterminacy itself. This implication is staggering. Collapse doesn't merely occur in spacetime, it actively reshapes spacetime as it unfolds. The feedback loop emerges naturally from this insight. Quantum uncertainty sources curvature, curvature enforces collapse, collapse amplifies uncertainty, and the cycle continues. Now we arrive at perhaps the most speculative and far-reaching implication of this framework, the idea that black holes are local collapse events within a universal wave function of spacetime itself. Some approaches to quantum gravity, particularly those inspired by the Wheeler-DeWitt equation, suggest that the universe as a whole can be described by a single wave function. This universal wave function encompasses all possible spacetime geometries, all configurations of matter and energy, every potential history. It's a superposition not just of particle states, but of geometric possibilities, different curvatures, different topologies, different shapes of space itself. The grand idea presented here is this: if the universe has a wave function encompassing all possible geometries, then a black hole represents a local resolution event. It's a place where spacetime is forced from a superposition of many possible geometries into a single, definite outcome. Look at the visualization, layers of overlapping geometric possibilities, all converging into the blue funnel at the center. The black hole is where ambiguity ends. Spacetime itself stops being in superposition and collapses into a specific configuration. The text on the right makes the unified collapse explicit. It's not just matter that collapses, geometry collapses, possibility collapses, all simultaneously. The black hole is a measurement event for spacetime itself, forcing it from quantum indeterminacy to classical definiteness. This perspective is profound. It suggests that black holes aren't anomalies or breakdowns, they are necessary features of a quantum universe. They're the places where the universal wave function resolves locally, where geometric superpositions reduce to single outcomes. In this sense, black holes are cosmic measurement devices, the universe taking stock of its own configuration. This idea points toward a future theory where spacetime itself is fundamentally quantum, with black holes as its natural measurement events. Every theoretical framework must be evaluated honestly for both its strengths and its weaknesses. This slide provides that balanced assessment. On the positive side, marked with a plus, this framework offers several compelling features. First, unifying intuition. It provides a simple, physically intuitive connection between quantum uncertainty and spacetime curvature, making the abstract relationship concrete through the feedback loop. Second, it acts as a natural regulator. The model resolves the singularity problem without requiring spacetime discretization or exotic modifications to geometry. The feedback dynamics themselves provide the regulation. Third, information retention. Rather than losing information, the model reinterprets the information paradox as reorganization. Information is transformed, encoded in the structure of the collapse process, and emitted through Hawking radiation. Fourth, the reciprocity principle itself. This offers a fresh, bidirectional view of the quantum classical relationship, treating collapse and curvature as mutually reinforcing rather than one-directional. But we must also acknowledge the challenges, marked with a question mark. First, mathematical underdevelopment. While the conceptual picture is clear, a fully consistent formalism describing this feedback loop doesn't yet exist. The equations remain to be written. Second, the collapse mechanism itself is speculative. The nature of wave function collapse is still unresolved in quantum foundations, making its collective, curvature-driven form even less well-defined. Third, testability. We can't directly access black hole interiors, making experimental verification extraordinarily difficult. Falsifiability depends on indirect signatures. This honest assessment shows that the framework is a work in progress, conceptually compelling, but mathematically incomplete, physically intuitive, but experimentally challenging. It's a hypothesis, not a finished theory, pointing the way forward rather than providing final answers. Despite the challenges, this framework is not untestable. In fact, it points toward specific areas where experimental and theoretical inquiry could probe its validity. This slide outlines those pathways. First, analog black holes. These laboratory systems, like Bose-Einstein condensates or fluid dynamics setups, can simulate event horizon physics in controlled environments. While they can't replicate true gravitational collapse, they can test the feedback dynamics between effective curvature and quantum localization. If the feedback loop is a real physical mechanism, we should see signatures of it in analog systems. Second, gravitational wave astronomy. The slide shows a spiral icon representing black hole mergers. When black holes collide, they emit gravitational waves, ripples in spacetime we can now detect. If black holes are feedback regulated rather than classical singularities, their merger dynamics might differ subtly from standard predictions. Searching for these subtle signatures in gravitational wave data could provide indirect evidence for or against the model. Third, quantum simulations. We can use quantum computers to model the feedback loop by simulating nonlinear Schrödinger equations coupled to effective curvature terms. If the predicted stabilization and regulation emerge in these simulations, it would lend credence to the theoretical framework. At the bottom, the slide lists how the theory could be falsified. This is crucial for scientific validity. The first falsification condition: if Hawking radiation is proven to be perfectly thermal and random, with no imprints of reorganized quantum information, the information retention claim collapses. The second, if singularities are proven to persist in all consistent quantum gravity models, the feedback regulator idea would be undermined. By clearly stating testable predictions and falsification conditions, this framework maintains scientific integrity. It's speculative, but it's also potentially falsifiable, the hallmark of good theoretical physics. We close with the central philosophical message of this entire framework: a complete reframing of what black holes represent in our understanding of reality. For decades, black holes have been viewed as places where physics breaks down. The singularity theorems suggested physical law ends at the center. The information paradox implied quantum mechanics fails at the horizon. Black holes seemed like cosmic embarrassments, places where our best theories give up. But this framework offers the opposite view. Black holes are not breakdowns, but convergences, climactic engines of reality transformation, where the deepest principles of physics come together most intimately. The symbol at the center, a beautiful interlocking pattern surrounding the black hole, represents this synthesis. It's not chaos, it's unity. The text makes it explicit. We propose viewing black holes not as sites where physical law breaks down, but as climactic engines of reality transformation, driven by a feedback loop between quantum uncertainty and spacetime curvature. This is where quantum mechanics and general relativity don't contradict each other. They engage in reciprocal exchange. The model emphasizes reciprocity. Quantum collapse shapes curvature, curvature enforces collapse. This bidirectional relationship is the essence of the convergence. And the final line captures the ultimate ambition. This perspective is a step toward a synthesis of quantum mechanics and general relativity, a picture where spacetime itself has a wave function and black holes are its measurement events. This is the vision. Not a theory of everything yet, but a conceptual pathway pointing toward one. A framework suggesting that the universe's most extreme objects aren't failures. They are laboratories where reality shows us how quantum and classical truly unite. Black holes, not the end of physics, but its most profound convergence.